Our growing use and reliance on computerized, automated systems has led to increased interest in the development and application of methods for defending against cyber attacks. The concern is that vulnerabilities may exist in unmanned autonomous systems that could easily be exploited by an adversary to compromise the effectiveness of an unmanned system and its missions. Cyber attacks on systems may come from a number of different sources, including attacks through the supply chain of components used in the system, insider attacks from people with access to the system, or malware attacks from corrupted software sources. We call the implementation of the system-aware cybersecurity designs the Sentinel, and we will demonstrate the Sentinel protecting an unmanned surveillance platform in this presentation. The Sentinel provides a secure monitoring capability that has been placed into the system in order to assure the operation of critical system functions identified as necessary in order to assure mission success. The secure Sentinel operates inside the system and utilizes system-aware cybersecurity design patterns to monitor a system's native data, compare it against the observed behavior of the system, and to identify potential cyber threats. Once a cyber threat has been identified, the Sentinel has the capability to either automatically address the affected systems by restoring the system to a known safe state, or alternatively, the Sentinel can alert the system operators to the identified cyber threat and present them with a set of related corrective actions. To demonstrate the system-aware cybersecurity concepts, an unmanned aerial vehicle, or UAV, was selected as a representative application. In this demonstration, the UAV is the Georgia Tech Research Institute's Unmanned Airborne Sensor System, or GAUSS for short. GAUSS is an outlaw ER UAV produced by Griffin Aerospace that has been modified for research purposes. The aircraft uses a commercial, off-the-shelf autopilot that provides stability and control for the aircraft. The autopilot system also includes an operator ground control station for mission planning and command and control. Researchers from the University of Virginia and the Georgia Tech Research Institute studied autopilot systems in general and identified several potential vulnerabilities that could be exploited by an insider or through a supply chain attack. Specifically, using a decision support method developed as part of the project, we identified key functions including GPS systems, payload control such as the camera Gimbal Controls system, and navigation waypoint parameter manipulation as possible targets for attack. We also ensured that the Sentinel itself is super secured against potential cyber threats. First, let's suppose that an adversary would like to trigger an attack whenever the aircraft enters a certain geographical area. This attack would change the current waypoints so that the aircraft would be prevented from conducting operations in a specific geographic region designated as a protected area by the adversary. Camera gimbal attacks are a group of uncommanded actions that are sent to the camera gimbal when triggered by some event, in this case flying through our designated trigger area. In our demonstration, we are showing the attack on and the protections for the gimbal system's ability to track a targeted point of interest. Shown here is an example of the gimbal's tracking system in normal operation where the point of interest, in this case a building, is normally tracked by the system. In our second pass, an exploit has been embedded which will deny the gimbal the ability to track an object in the trigger region without any protections. The operator tries to engage the tracking system, but the attack forces the camera to retract, rendering the tracking and the video collection capabilities inoperative. In our third pass, the operator again tries to track an object inside our attract trigger area. Only this time the Sentinel is in place, verifying the tracking capability of the gimbal, and blocks the attack, allowing normal tracking to occur. The security operator is then notified of the attack and the restoration, and the data related to the system and the attack is collected for forensic purposes. Waypoints are key parameters that describe a specific flight plan used to control the navigation of the Gauss UAV. As a result, they offer a tempting target to an adversary to control where the platform would and would not be able to gather intelligence information. This demonstration will show a few alternatives available to an adversary for compromising the waypoints, as well as protections defending against those attacks. First, we show that the system-aware sentinels are able to identify a normal change, that is, a change made by the operator of the UAV aircraft system, to the existing flight plan. The operator executes a normal action on the operator station that sends the aircraft from one flight plan to another, meaning redirecting that aircraft from performing surveillance in one area to another area of operation. Specifically, the operator will select a new waypoint, in this case, waypoint number 11. While this is occurring, the air sentinel will be monitoring for deviations to the existing flight plan, while at the same time, the ground sentinel will be monitoring the operator's activity to see if there's a match between the waypoint change in the air and the activity on the ground. In this case, the change is determined to be normal. Because we are protecting the navigation parameters, the cyber operator is notified of the normal change and the flight continues. For the second pass, we will inject an attack that will redirect the aircraft to a new waypoint during our flight. Our adversary has embedded an attack in the autopilot hardware that is triggered by our geographic location and which will change the waypoint to redirect the aircraft away from our area of interest. As the aircraft enters the region, a new waypoint is injected into the system by malware embedded on the autopilot, and the aircraft diverts, in this case to waypoint number 11 on a different flight plan. The Sentinel detects the change, but does not find a corresponding operator action on the ground, and therefore sends an alert to the Cyber Commander workstation. In this case, there is not a masking component into the attack, so that it is obvious to both the operator and to the cybersecurity operations personnel that the attack is underway, and the Cyber Commander is given the option to redirect the aircraft back to the original waypoint and back on the gold standard flight plan, or anywhere else in the flight plan action. Other options for corrections could be provided for the Cyber Commander, such as allowing the attack to continue so as not to tip off the adversary and to allow for the collection of forensic data to gain intelligence about the attack strategy. This last pass includes an attack on both the air and the ground systems simultaneously. Similar to the second pass, the embedded attack will alter the waypoint in the air. However, this time our adversary will have also attacked the operator station so that the attack is masked from the operator. The Sentinel alerts the Cyber Commander workstation to the attack. We see here that the Cyber Commander is showing the actual version of the flight plan that the aircraft is currently flying, while the operator station is showing a masked version. If the Sentinel was not in place, the adversary would have full control to fly the aircraft to whatever area they desired, and the effects would be hidden from the operator until it was too late. The Cyber Commander is presented with the ability to restore the waypoint and the flight plan back to the original plan, or to choose to fly the aircraft to whatever location they designate.